Today I'm going to be talking about the California nitrogen assessment, and this was an effort to synthesize what was known and not known about nitrogen flows, management, and policy in California. And major funding for this came from the David and Lucille Packard Foundation, and it was run through the Agricultural Sustainability Institute at UC Davis. And I'm excited to be talking about it right now because just finally, after what seemed like a long time, the final publication is finally out this month. It's available from UC Press and available on Amazon. And any day now there'll be an executive summary that's available. And then next month there'll be legislative and public briefing, and then a series of outreach events for around the state for stakeholders. And as a way of introduction, I'll address a couple of questions about why California, why nitrogen, and why assessment. And why California is easy. Everything is here in California. There's agriculture, there's people, there's beautiful places, and so anything that you'd want to study related to nitrogen is here. Secondly, why does nitrogen matter? And the easy answer for that is it's essential for life. So every living thing needs nitrogen. It's the cornerstone of agricultural productivity. But nitrogen is a slippery element in that once it's been fixed in reactive forms from N2 in the atmosphere, it can be readily transformed and transported in ways that are difficult to control. And so whether the fixation happens intentionally for production of fertilizer and food production, or by the growing of leguminous crops, or unintentionally through the burning of fossil fuels and the production of NOx and ammonia and N2O from that, there's the potential for it to leak out into the environment where it can cause problems both in the air and surface waters and in groundwater. And so once nitrogen has escaped into the environment, really the only way that we can try to control it is to increase denitrification, which turns that reactive nitrogen back into N2 in the atmosphere. And this happens in a highly controlled way in wastewater treatment plants, and much more haphazard way in soils and in aquatic sediments and in groundwater. And then finally, from a regulatory and a policy perspective, nitrogen is a real challenge because it's used everywhere in a lot of different ways, and it affects both air and water, which are typically regulated separately. So finally, what is an assessment? And so this is an approach that's in a critical evaluation of information to guide decisions on complex public issues in response to stakeholder questions. So some international assessments you might be familiar with are the IPCC assessment of climate change or the Millennium Ecosystem Assessment. But assessments are conducted in a credible, useful, and legitimate, so this means an open and transparent way, and that they're policy relevant but not prescriptive. So the idea is to give a range of options but not recommend any particular ones and let the stakeholders decide what to do with the information. And then finally, the assessment is peer reviewed by the stakeholders and researchers and experts in the field. And so we started this process by organizing a group of stakeholders around the state of California that involved government agencies, commodity groups, a variety of agricultural interests, fertilizer industry, environmental groups, and we went to them and asked them, what are your questions related to nitrogen? And we organized those questions into several overarching questions for the whole assessment. So those questions were, what are the big sources of nitrogen pollution in California? What practices are most effective in mitigating nitrogen pollution? What are the policy challenges and opportunities? And what are the impacts of nitrogen management on society and human health? And so we took those questions and organized them into four main chapters of the assessment. So we looked at the drivers of nitrogen use. We calculated a statewide mass balance of nitrogen, and that's what I'll be focusing on today. We looked at impacts of nitrogen on ecosystem services and human well-being. And then finally, technological and policy options for dealing with nitrogen. And so specific to the mass balance, there were questions that we addressed in that. And so those were, what are the relative contributions of different sectors, so agriculture versus transportation, to nitrogen cycling in California? What are the relative amounts of different forms of reactive nitrogen in air and water? So how much NOx, how much ammonia, how much N2O, how much nitrate, how much ammonia, ammonium. And then finally, are measurements of gaseous losses and water contamination accurate? And so there's a lot of discussion about nitrogen in California, about who's to blame for the nitrogen problems. And that was not our goal, was to assign blame in California, but our goal was to document what are the relative amounts of nitrogen that are used. And so the mass balance approach is a pretty simple one. It's just an equation of the inputs to your study area, so the amount of new reactive nitrogen, so anything but N2 that's entering your study area, has to be balanced by the outputs in the storage, so nitrogen leaving the study area or nitrogen accumulating within the study area. And we can use this to compare the relative size and directions of flows of nitrogen in the state. And so, but we treat the whole state of California as our study area, so it's not spatially explicit. We use spatially explicit data, but the final calculations are just for the whole state of California. And so what we come up with is what I refer to as the spaghetti diagram. I'm not sure why it's a little bit out of focus here, I think. But the basic idea that I guess you can't see is, so we draw a box around the state of California. So it includes the geographic borders of the state, the coastline of the state, but it includes the atmosphere above and the subsurface and groundwater below the state. And so any new reactive nitrogen that's coming into the state of California is considered an import of nitrogen to the state. And then all of these blue arrows within the state represent flows of nitrogen within the state. And so we've defined 8 subsystems within the state, and we calculate flows between all of those as well. So the atmosphere, natural lands, croplands, urban lands, surface water, groundwater, people and pets, and livestock. So we calculate the flows of nitrogen among all of those subsystems. And then we calculate the nitrogen shown in the red arrows that's leaving the state. And so when we do that on a statewide level, we come up with 1,626 gigograms, or 1,626 million kilograms of nitrogen per year. And we divide that up among the possible sources, or among the various sources of nitrogen coming into the state. And so by the largest source of new reactive nitrogen to the state is synthetic nitrogen fixation. So this is the industrial process by which nitrogen is fixed from the atmosphere into ammonia. And the largest fraction of that goes to fertilizer. Some of that does go to other industrial uses. Next is fossil fuel combustion. So this is the unintentional production of NOx associated with fossil fuel combustion, with electricity generation, with transportation, any fossil fuel combustion. 12% of the new nitrogen coming into the state is from feed imports for livestock. 12% is from the biological fixation of leguminous crops in the state. And then the brown bar says 9%, that's the biological fixation in natural lands in the state. And so what that suggests is that because of human activities, we have about 10 times more nitrogen coming into the state every year than we would have in the absence of human activity. And a few other smaller inputs of nitrogen to the state as well. And then at the state level, if we look at what's happening to that, a large fraction of that NOx combustion that goes up into the atmosphere just blows downwind out of the state. So 17% of the nitrogen that comes into the state blows downwind out of the site, blows downwind out of California. Next in the pie chart, 16% for groundwater storage. So a large fraction of the nitrogen coming into the state is ending up in groundwater. And some of that is due to the hydrology in California and the geographic setting, but and where nitrogen is used. And then a whole bunch of other losses, both gaseous losses of N2, ammonia, and N2O, and then relatively small dissolved losses of nitrogen. So relatively little nitrogen going out in the rivers, relatively more actually going out directly as wastewater from sewage treatment plants than in all of the rivers combined in the state. And then one of those green bars at 5% is the amount of food that's exported from the state. So we do produce relatively more food than we need to feed all the people in California, but we do import livestock feed. So then starting to think about some of the systems within California. So we'll look at a few of these subsystems related to agriculture. So the first one is cropland. So when we look at what are the inputs to cropland in the state, by far the biggest one of input is synthetic fertilizer. So industrial fertilizer accounts for about half of the nitrogen applied to cropland. And then about 25% of the nitrogen is coming from manure. So this is a recycling of nitrogen from the livestock subsystem that goes back out onto the fields. And then about 20% of the nitrogen is coming from biological fixation. In California, it's almost exclusively alfalfa. And then smaller amounts from nitrate dissolved in irrigation water, atmospheric deposition, and the application of biosolids, or the leftovers from wastewater treatment. When we look at what's coming out of croplands, about 35% of the nitrogen harvested goes to feed for livestock, and 18% gets harvested for food for people. So a little more than half of the nitrogen that's applied to cropland is harvested, but about a third of it is leaching to groundwater, and then smaller amounts, once again, to gaseous losses and to surface discharge. If we look at the livestock subsystem, California grows enough feed for about 2/3 of the needs of livestock in the state. And then that livestock, of the nitrogen that gets fed to the livestock, about a quarter of it ends up in food products, so both meat and dairy products. And then about 75% of that becomes manure, some of which is volatilized and some of into the air, and some of which is applied to cropland. And then finally, the last subsystem I'll talk about today is the groundwater. And so by far the dominant source of nitrate to groundwater is from cropland. So almost 90% of the nitrate to groundwater is coming from cropland. Much smaller amounts from natural leaching in natural lands. The manure in this case refers to leaching from the confined or from the dairy facilities themselves, and then a small amount of sewage nitrate reaches the groundwater as well. And that's both from septic systems and from land-applied discharge from wastewater treatment plants. Of nitrogen that's coming into groundwater, a small amount is pumped back out as nitrate in irrigation water. About a quarter of it we estimate is denitrified, so turned back into N2 from that nitrate pool in groundwater. But about 2/3 of that nitrate in any given year is accumulating in the groundwater. So a couple 100,000 kilograms of nitrogen are accumulating in groundwater in the state of California every year. And so I'll just touch on a few of the other aspects of this. So this cartoon shows the fates of these flows of nitrogen in a slightly different way. So the colors represent the form of nitrogen. So the dark brown is emissions of NOx or ammonia. The kind of teal color is emissions of N2O from these different land uses, so from urban lands, croplands, natural lands. And then the orange colors below represent leaching of nitrogen to groundwater and surface waters. And the relative size of the arrows indicates the size of the flows. And so agriculture, once again, dominates with a large amount of nitrogen going into the air from ammonia volatilizing from manure, and then a large amount of nitrate flowing from cropland into groundwater. And so there's, once again, numbers on all these flows and no error bars, and we tried to do multiple estimates for all of these flows using independent data sources, but we didn't try to calculate an actual error bar for any of them. Instead, we used the uncertainty approach that the IPCC uses, where we put the uncertainty in this matrix where we're looking at the level of agreement of all of the evidence for the various flows, so low agreement, medium agreement, high agreement, and then the amount of evidence for all of these flows. So is there limited evidence, medium evidence, or high evidence for these various flows? So you can see most of the flows are on the left-hand side of the diagram. So we have relatively limited or medium evidence for a lot of these flows and relatively low agreement. So there's definitely, we use the best numbers we could find, but there's definitely a need for better numbers. And then finally, to finish up, I'll just touch on some of the other parts of the assessment. So we looked at nitrogen's role in ecosystem services and human well-being. And so one thing that comes up is there's a lot of benefit from nitrogen use in agriculture. There's no denying that, but there's also a lot of downsides to nitrogen in terms of clean air and clean water. And a lot of these are overlapping in spatial scale. And so there's parts of the state, so especially in the San Joaquin Valley, where there's a lot of air pollution and water pollution. And then in terms of management and policy related to nitrogen use, we identified three strategies for reducing nitrogen-related problems. So reducing inputs of new nitrogen, targeting specific transfers of nitrogen between these subsystems, and then finally potentially adapting to nitrogen-rich environment. And so a lot of the practical approaches that, once again, we're just looking at existing technologies have to do with increasing nitrogen use efficiencies, whether it's in cropping systems or in animal production systems or in the transportation or energy sector. And these types of mitigation strategies sometimes involve trade-offs where by reducing nitrate leaching to groundwater, it might increase nitrogen gaseous emissions to the air. And there are certain barriers to the adoption of these, whether it's cost or logistics or information or regulation that prevent the use of these. And so just to finish, that's interesting, it's not showing up. So there's certain policy challenges and opportunities that are available related to nitrogen. And we suggest that nitrogen might be a good candidate to pioneer the next generation of integrated environmental policies and regulatory reorganization. Because nitrogen touches on so many policy issues and it involves so many different regulatory frameworks, it might be a stimulus to rethink how we're addressing some of those. But it's a problem because of the complexity and diversity and spatial dispersion of the problem that a lot of times there's high transaction costs associated with addressing nitrogen. And then finally, how the nitrogen policy is designed and implemented might be as important as what the policy targets. So getting all the stakeholders in the room to talk about these issues can really help looking at just figuring out how to address these nitrogen problems.
Thank you, Daniel. We've got time for one quick question.
Thank you, Dan, for your presentation. About the accumulation, which is quite a large amount, it is a result of a calculation, or it is based on the nitrate measurements in groundwater, or changes in soil organic matter?
Yeah, so there were three different ways we tried to estimate nitrogen in groundwater. One was just looking at other studies who had found, they're mostly from Europe, studies that found about 40% of, you were talking about denitrification or so it's a balance of the inputs and the outputs. And so on the input side, it's kind of a fraction of the fertilizer applied from leaching studies that was found to get below the rooting zone. as well as, now I'm forgetting the second approach. And then on the other side, on denitrification, it was using literature estimates from other studies that found about 40% of nitrogen was denitrified in groundwater, combined with some half-life data from California specifically, and concentration-based estimates of denitrification rates. So some data sources specific to California, some not necessarily, but a couple different approaches to looking at that.
Thank you.